Thanks for joining us for this brief introduction and demo into Backtrace. Backtrace is an error monitoring and software quality management platform. The state of the art today for software error monitoring is broken. Software errors can come in many forms, from core dumps and mini dumps that come out of your application runtime, to CI/CD build pipeline failures, or defects raised in static code analysis tools or memory error checkers. Errors are going to come from many different sources, from back-end servers or containers to desktops, mobile devices, or even embedded and IoT devices on the edge. Developers need more than just a stack trace or log entry in order to resolve these errors. They require context, such as custom metadata, environmental information, and other types of attachments. And many errors can't be solved in isolation, requiring collaboration with different team members and the ability to drill deep into the information and analyze larger corpuses to understand what's been going on. Backtrace is a complete platform for managing all your software errors. It does full-stack monitoring, meaning cross-platform, cross-environment, cross-language monitoring of errors, crashes, or other types of software defects that you can detect. The web-based debugger provides all the context that the engineer needs in order to help debug the issue at hand, including fully symbolicated call stacks, all of the contextual metadata that's been associated to the issue, environmental variables, and any sort of attachments that were included. Backtrace integrates fully with your workflow tools such as Slack or Microsoft Teams for chat, Jira or GitHub Issues for task tracking, Datadog or Circonus for monitoring and APM, PagerDuty and OpsGenie for alerting, and so on. One of the unique values of Backtrace is its ability to allow you to query and search by any of the attributes that you customizably capture or that the system automatically captures. It also provides full data scrubbing capability, so any PII or personally identifiable information is easily scrubbed from submitted dump files, memory and environmental regions, and so on. The system provides full retention management, so you decide how long you want to retain software errors for, and it's fully flexible with its deployments. So our customers can deploy on-prem, in one of our multi-tenant hosted environments, or on a dedicated hosted instance that we provide on the cloud provider of their choice. Over the next few minutes, we'll show you a demo of the Backtrace system, highlighting some of those key capabilities that we just discussed. The environment we'll be showing you is our own internal Backtrace instance that we use for monitoring all of the products that we produce. All right, we're going to start off here in our Backtrace internal instance. Again, this is the instance that we are using to monitor all of our in-development and all of our production applications. The way Backtrace works is that software errors are submitted to various projects. Here's a list of projects on our instance here. Usually a project is set up as a container for all of the software errors related to a releasable artifact. In this case, you can see here the Coroner project is our Backtrace object store and database written in C, running on Linux servers. We've got other applications such as our CrashPad application written in C++, or some of our other services such as our SAML service or share service written in Node or Python here. In addition to a project being a container for a given releasable artifact, a project can also contain software errors related to continuous testing suites. So our CTS project here is used for all of our automated testing of our CI builds where memory error checks, race condition checks, static code analysis, defects are all stored and referenced for future work. We'll dive into our Coroner project. This is the Backtrace object store and database. We store all software crashes from pre-production as well as all of our deployed instances here. As we open up the project, let's just dive right into the debugger so we can discuss some of the advanced Linux debugging capabilities that we've developed. The debugger provides me with a way to view all of the context around an error report that's been submitted. We see a list of all of the threads that were captured as part of the core dump, and a call stack related to each of those threads. The web debugger has a lot of intelligence built in, so you can jump directly to the faulting frame, view values of local variables, see classifiers of the type of issue that the debugger detected, and view annotations which give critical and warning messages to help indicate what may have gone wrong. This in and of itself is a generational leap in debugging technology. The ability to provide this level of analysis, annotation, and summarization on error data is one of the key reasons our customers see dramatic reductions in mean time to detection and resolution of these software quality issues. Let's dig into some of the additional context that we can see down below. Here we have a list of all of the metadata that was submitted alongside this error report. In this case, the application name, which host it was running on, the version, as well as the process age, how long the application had been running. Other information is available to me here as well, such as the context of the heap and system-related information. I also have the ability to add comments, which can help annotate and support collaboration activity. We could see here our colleague Sammy has indicated that this issue was related to the file system being full. Let's say we wanted to explore the system some more to find other similar crashes or other things impacting this host, or just understand more about the crashes and errors impacting our Coroner system. So we'll dive into our Explore view here, and we're going to build a new report or a new saved view. We're going to group by host name, and we're going to start to add some aggregate values here. We'll list the unique number of fingerprints or unique number of issues we've seen for each host. We'll show a distribution of the call stacks impacting that host, and a distribution of the versions of Coroner that have been deployed to that host. Finally, we'll add some timestamp related information so we could start to sort this data based on most recently impacted hosts. So now we have a list of hosts sorted by most recently impacted with a crash. You can see the host that was impacted, the number of issues that have been seen on that host, the unique number of issues, and then the distribution again of the call stack and the version. Let's say we wanted to dig in to one of these hosts in particular and see specifically which issues had impacted it. So we'll hover over the host we're interested in, and we can right-click and see the context menu where we can apply a filter to action. You'll see up in the filter bar, we've applied that host name. And if I click over on my triage tool now, I can see I have 3 unique issues on that host, 1 that's open and 2 that we've muted. Let's switch back over to our Explore tool so we could dig into this data a little bit more. Let's say instead of being interested in a particular host, we're interested in startup issues. Those where the application was running for less than 5 minutes or less than 300 seconds. So we'll apply that filter here. And we'll see a list of all hosts that have had crashes within the first 5 minutes of runtime. If we change the time filter here and go to just over the last 30 days, we'll see that there's 1 production host that has seen an issue, but all the rest are our in-development hosts. We'll show one more example of what you could do here with our Explore view. Let's say we're interested not in instability by host, but actually instability by application module, because I want to work with my engineering managers who are responsible for each of these modules so they understand instability in their area. You'll also see that we can save these views. I have a few already created here, and make it accessible for everyone on my team to be able to see. One other feature of the console I want to show you is our flame graph visualization. It's accessible here in the Explore tool under View As. And when we click on it, what we'll see is instability by code path. This is showing us which functions were involved in faults or crashes or errors in my running application. I could drill into one of the frames here to expand and see issues that are going through the same piece of code. This is useful if I'm doing maintenance on certain areas of the code and I want to try and group together all of the issues that are impacting it. We spent a lot of time here in our web console. Let me show you a few other ways that engineers can get access to this software error information. I'm going to jump over to a communication tool over here, Slack. Now this could easily be Microsoft Teams or IRC or any other communication tool. Here I see a list of new incoming software errors for one of the projects that I am monitoring right here in my Slack window. I can see which project it was related to, information about the call stack, and then all of the contextual metadata that we've collected. What type of error is this? What GPU is in use? What engine version is being run? And other custom attribute information that's useful to understand the issue. From here, engineers can very quickly get back to that web debugger view where they have insight and annotations, the ability to comment and collaborate with other team members, and even the ability to link to issue tracking systems like GitHub Issues or Jira to track this effort and get to work.